let's talk about solving systems of linear equations by using the inverse of a matrix. To get there, though, let's start by this multiplication problem. Suppose we have A equals 12, 5, -7, 3. And I have another matrix that I'll call I that is 1, 0, 0, 1. Well, if we multiply A times I, we know A is on the left. We have 12, 5, -7, 3. And we're multiplying that by 1, 0, 0, 1. And I'm assuming that you have already practiced how to multiply matrices together. Remember, this row and this column will be used first. So I have 12 times 1 plus 5 times 0. So that's 12 plus 0, or just 12. I'm going to move on to the second column here. So 12 times 0 plus 5 times 1. That's 0 plus 5. Now I'm using my second row, first column, -7 plus 0. And second row, second column, 0 plus 3. And you'll notice this is actually A again. So when I multiplied A by this matrix I ended up with A. We know that multiplication of matrices isn't commutative. So what happens in this case, though, when I put the I first? 1, 0, 0, 1 multiplied by 12, 5, -7, 3. And here we go. We have 12 plus 0. 5 plus 0. 0 plus -7. And 0 plus 3. And again, we end up with our matrix A. So when we began with A, it didn't matter if we multiplied by I second or multiplied by I first. It didn't change the value of our matrix. I think of it much like multiplying by 1 in arithmetic. If you start with a 5 and you multiply by 1, you get right back where you started from. We call this our multiplicative identity. Similarly, when you multiply by this identity, we end up with the same matrix that we started with. Our identity matrices look like this. I'll put a little subscript 2 here so that we know it's a 2 by 2 matrix. Our identity matrix is a matrix that has 1s along the main diagonal and 0s everywhere else. And our main diagonal is from upper left to lower right. So another identity matrix, our 3 by 3 identity matrix, would have 1s along this main diagonal and 0s everywhere else. So if you were to multiply a matrix by this identity matrix, again, your original matrix would be unchanged. So now let's set that aside for a minute and let's move on. Let's talk about multiplying these matrices together. I'm going to let A equal 2, 1, 5, 3. And I'm going to let a matrix B equal 3, -1, -5, 2. And let's just find their product. So I'm going to find AB. So I'm writing A first. It's 2, 1, 5, 3 times 3, -1, -5, 2. And here we go. We're using the first row, first column. So we have 2 times 3 plus 1 times -5. So 6 plus -5. That's a 1. First row, second column. -2 plus 2. Second row, first column. 15 plus -15. And last, -5 plus 6. And you'll notice that I ended up with the identity matrix. A times B is equal to I. Let's see what happens if we write them in the other order. What if we have B times A? So we have 3, -1, -5, 2. And we're going to multiply it by 2, 1, 5, 3. Here we go, first row, first column. 6 plus -5, that's a 1. 3 plus -3, that's a 0. -10 plus 10, another 0. And -5 plus 6, that's 1. And again, I have the identity matrix. So we see that A times B is equal to B times A, which equals I. That means A and B are inverses of each other. So we could say B is the inverse of A. And again, if I go back to arithmetic, I think of this, 5 times 1/5 equaling 1 as the arithmetic version of what's happening here. That's my multiplicative identity. These are called reciprocals, but they are also called multiplicative inverses because when you multiply them together, you end up with the identity. So B is the inverse of A. Didn't leave a very big space right there, but we can write it this way. B is equal to A inverse. So we would write this, A times A inverse equals I, and always A inverse times A would equal I as well. When you multiply inverses together, you will always get the identity matrix. Well, you know, the question comes up, well, why is this even useful? Or how is this useful? Well, let me give you a couple of other inverses. Suppose we knew this. We have A equals 4, 7, 1, 2. And A inverse is 2, -7, -1, 4. Now you could multiply those together and confirm that they're inverses, and I'm not going to take the time to do that though, but you could. Let's suppose we were going to solve this system. It is 4x plus 7y equals 31, and x plus 2y equals 9. I'm going to write this system of linear equations as a matrix equation. That means I'm going to look at the coefficients of x and y. I have 4, 7, 1, and 2. 4, 7, 1, and 2. I'm going to multiply that by this matrix here that represents the variables x, y. And it equals the constants, 31, 9. And you could confirm, multiply this 2 by 2 matrix by this 2 by 1 matrix, and you would get this. Notice here that this is the matrix A. So I have A times, and let's let this matrix that has the variables in it, let's call that X, capital X because it's a matrix, equals, and we'll call this B. This matrix that contains our constants, we'll call it B. Our task is to solve for X. So I'm going to do that by multiplying by this equation by A inverse. And when we're working with matrices, you know the order matters. So when I multiply by A inverse on the left here, I must multiply by A inverse on the left here as well. So A inverse times A, we saw previously, that's just your identity. And your identity multiplied by any matrix just gives you that matrix back. So let's see what that means. That means for this particular system, the matrix XY equals A inverse, which we were told is this. Let's write that down. 2, -7, -1, 4, multiplied by B. B is 31, 9. And if we do that multiplication, we would have 62 minus 63, that's -1. -31 plus 36, that's 5. And we know when matrices are equal, their corresponding entries are equal. So we know x equals -1 and y equals 5. So the solution to this system is -1, 5. Now let's do another one. Suppose we have this system. It is 4x plus 2y plus 3z equals 1. And 3x plus 3y plus 2z equals -2. And x plus z equals 10. Now, our A would equal the coefficients of our variables. So A would be 4, 2, 3, 3, 3, 2, 1, 0, 1. Now let me just tell you what the inverse of that matrix is. It's equal to this. 3, -2, -5, -1, 1, 1, and -3, 2, 6. So if we were going to solve this system, we can still use the fact that x, which is our column matrix that represents our variables, equals A inverse times B. So x, y, z equals A inverse, which we know is this, 3, -2, -5, -1, 1, 1, -3, 2, 6, multiplied by B. B, remember, is your set of constants, so, or your matrix representing those constants. So I have x, y, z equals, and now I need to do the matrix multiplication. I have 3 plus 4 plus -50. 3 plus 4 is 7, plus -50 is -43. -1 times 1, -2 times 1, and 10 times 1. So -1 plus -2 plus 10 is 7. And last, -3 plus -4 plus 60 is 53. So we know the solution to this system is the ordered triple, -43, 7, 53. So you can see that if you know the inverse of this matrix A, solving the system is pretty straightforward. Well, how do you find this inverse of the matrix? That will be the topic of the next video.